Hello, my name is Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering, and this is my module on the spectrum of a digital communication signal. So there's a couple of reasons why understanding what a communication signal looks like in the frequency domain is so important. The first is, or the first reason comes up when you're transmitting through a channel with a low pass characteristic. So let's say you're transmitting your signal through some kind of cable, coaxial cable, Ethernet cable. Regardless of the cable type, they all exhibit a low pass cutoff characteristic, and better cables have the cutoff occurs at a higher frequency, but they all eventually do attenuate the signal at higher frequencies. And as you increase the bandwidth of your signal, if your signal starts to overlap with this cutoff region, that component of your signal gets attenuated, and the result is distortion of the signal in the time domain. Another reason why we need to understand what our signal looks like in the frequency domain is for wireless communications, because the wireless spectrum is very, very tightly controlled and regulated by most governments. And if you're designing a wireless communication system, you will be told the range of frequencies that you're allowed to transmit in, and most standards will define what they call a spectral mask that will say, how powerful your signal can be at certain bandwidths. And it's important that you design your signal to fit within that spectral mask. And so we need to have an easy way to understand what our signal looks like in the frequency domain, and we need to understand what properties of our signal we can change in order to change the shape of the signal spectrum. And so that's what we're going to be concentrating on in this module. Now, in this module, we are going to be deriving the power spectral density of the communication signal. The reason why we focus on power spectral density is because communication signals are modeled as random stochastic processes, because we model the information bits as a random stream of ones and zeros. And so we'll be focusing on a PSD, or power spectral density derivation. And we're going to be focusing specifically on a baseband signal. But as we've seen in our signal representation module, passband signals can be represented in baseband as well. And so that means the derivation that we'll be doing here can be used to represent passband signal spectrum. All you have to do is just take that baseband signal spectrum and shift it up so it's at plus or minus the carrier frequency. The first thing I'd like to do is introduce the signal notation I'll be using. Our transmitted communication signal is S of t, and I'm using kind of a short form of signal vector notation. So we have a series of time-shifted basis functions f, and you'll see I've dropped the subscript on the basis function, multiplied by a signal vector value s of n. Now, what's different here is rather than just looking at one symbol, which is what we typically do when considering signal vectors, I'm considering a train of transmitted communication symbols. And so the best way to visualize this, or the easiest way to visualize this, is as a binary PAM system, for example, where F is perhaps a square pulse, and S is all of the signal vector values that flip that square pulse between, let's say, +1 or -1. Now, the subscript on S, the subscript on the signal vector value N, doesn't indicate the modulation symbol index anymore. Instead, it's a time index. So S1 would come after S0, S2 would come after S1, and so on. So the first step when finding the power spectral density of a signal is to find its autocorrelation. And so the autocorrelation term is here. And we're starting with the general autocorrelation. That's a function of some time value t and some time value shifted by a value tau. And autocorrelation of any stochastic signal is equal to the expected value of the signal conjugate multiplied by the signal at the time shifted value. And this 1/2 term is there because we're assuming that in general the signal could be complex, right? So that would be the case if we had a 2 basis function signal, maybe if we were representing PAM or QAM at the baseband. And so all we do for the next step is to just substitute in our signal expression and shift around the summation a little bit. And so to get to this, I guess, second equation here, there's a couple of tricks that I did. The first thing was to move the summations for the 2 signals out front. And then you'll notice that the expected value operator I have shrunk so that it's only around the signal vector values. And that's a fairly standard trick that you can do when dealing with equations that have some components that are random and some components that are not random, right? So the thing that makes a communication signal random is the random information. And that means that the signal vector values which reflect the information are the random parts, but the basis functions are not random. Those are just, if we're thinking in terms of PAM, those are just the pulse shapes, and so those can stay outside of the expected value. So the expected value operator gets to sort of shrink around the random component. And then to get to the final equation, all I've done is replace the expected value of the 2 signal vectors with just a functional notation, which is meant to represent the autocorrelation of the signal vector values, right? So the expected value of the signal vector at an index n multiplied by the signal vector value at a time index of m. Now, in general, there could potentially be correlation between information symbols, information signal vector values at different times. So for example, if we look at the expected value of, let's say, S0 multiplied by, I don't know, maybe S4, right? This is going to be equal to 0 if S0 and S4 are statistically independent. And that's typically the case. In general, we assume that the information transmitted by one symbol has no correlation or is completely independent of the information transmitted by another symbol. The only time when this isn't true is when you use some form of code, which applies some memory to the signal. But we're not really going to get into coding at this stage, so we generally assume that information is independent. And because of that, we assume that the autocorrelation of the signal vector values is equal to the energy per symbol multiplied by a discrete delta function. And so a discrete delta function, n, is always equal to 0 for n not equal to 0. And if n is equal to 0, then the delta function, I'll just put a 0 in there, is equal to 1. Now, if the delta function is equal to 1, that means that that we're correlating the same symbol, clearing away the notation. So remember that our original expression was n minus m, which is equal to the expected value of Sn Sm. Now, if we are correlating the signal with itself, then we have, or if we're correlating a signal vector with itself, then the indices n and m are the same. And then we have basically the conjugate of the signal vector value taking the expected value, which is just equal to the average energy per symbol. Right? So that's why we have this energy per symbol term in front of the delta function. Now the last thing that I want to do in this slide is just do a bit of a variable substitution. So we're going to let k equal to m minus n, and I'm going to substitute that into the equation on the previous slide. And when you do that, the autocorrelation of the information symbols become simply a function of k, and we can pull it out front by itself, which, as we're going to see later on, helps us in the derivation. And then we have the multiplication of the two basis functions by themselves as well. And so this sets us up for the next stage of the derivation, which is dealing with the unusual stationarity of a communication signal. Now, if you think back to sort of basic stochastic theory, we've talked about, the stationarity of signals, and one sort of standard type of stationarity is wide sense stationary signals. And a wide sense stationary signal is one that has a mean that is independent of time and that has an autocorrelation function that is a function just of the shift in the two time values that you're comparing, but not the actual absolute location of those two time values. And so we say that the autocorrelation is sort of shift invariant. The unusual thing about a communication signal is that it's what's known as cyclostationary. So it has a mean and an autocorrelation that does change as a function of time, but it changes, but both functions turn out to be periodic. And so cyclostationarity is most easily illustrated by looking at the mean. The autocorrelation function is a little bit more complex, but we can look at the mean, which is relatively straightforward. And so again, a cyclostationary random signal is one where both the mean and autocorrelation functions are periodic with a period of t, which is equal to the symbol time. Now, if we just consider the mean, so we take the expected value of our transmitted signal. This is a typo. This should be s of t, not x of t. We take the expected value of our original transmitted information expression. And again, we do the trick that we did a couple of slides ago, where we take our expected value operator and allow it to sort of shrink around the part of the signal that is stationary, or sorry, that is random. And so the only term in this equation that's random is the signal vector values, and so we take the expected value of the signal vectors. And so let's consider an example. Let's consider a triangular pulse on-off keying PAM scheme. And on-off keying is where you transmit the pulse shape to represent a 1, and when you want to transmit a 0, you transmit nothing at all. And so your signal vector values are equal to some positive value for a 1, and then the signal vector is for a 0 is equal to 0. And so when you take the mean of that, the expected value of those signal vectors, you get some non-zero value. And so this term that I've circled would be some constant. And then this overall expression ends up being just some constant multiplied by the shifted pulse shapes. And so the expected value of this triangular pulse on-off keying scheme would just have a mean that looks like this. Now clearly this mean is not constant, right? So we can't say that this signal is wide sense stationary. But because it does repeat, it is, again, what we call a cyclostationary signal. Now, when presented with a cyclostationary signal, the standard trick is to average out the periodic variation. And so what we're going to do is we're going to come up with an averaged version of our autocorrelation, which is just equal to our original autocorrelation expression integrated over the symbol time, and then multiplied by a normalization factor of 1 over t. So we're just going to use an integral to kind of average one period of our periodic autocorrelation function. And so then the next expression, which gets a little bit more complicated, is I'm going to take
the expression for our autocorrelation from the previous slide and plug it into this integral, right? So out front, we've got the summation of the autocorrelation function of our signal vector. I can pull that in front of the integral because it's not a function of time, right? Where we're integrating with respect to time. Same thing with the summation with respect to n. It's also not a function of time, so I can pull it out front. And then we can take our integral and let it operate on the only two terms that are a function of time, which are the two shifted pulse shapes. So the next thing then I want to do is play a little bit of a trick where I take the index nt and I pull it into the integration index, right? So I take the nt term and then I plug it into the integration index. So I basically shift the integration index, and so that allows me to pull nt out of both this location and this location. Now, what happens, or the reason why I want to do this, the benefit of this, is let's take a look then at the integral and the summation together. So the integral and the summation together are equivalent to integrating from plus or minus infinity, because we integrate from from t over 2 to minus t over 2 at some value of nt, and then we add it to a shifted version of that, and then add it to a shifted version of that again. So again, for example, if n was equal to 0, we integrate from minus t over 2 to t over 2. When n is equal to 1 in the summation, we integrate from minus t over 2 minus t to t over 2 minus t. When n is equal to 2, we integrate from minus t over 2 minus 2t to t over 2 minus 2t, and then we keep adding these terms together. And so the summation and the integral argument working together is just equivalent to integrating from minus infinity to infinity. And so what we can do then is replace this whole term with the function phi f, which is just the integral of from minus infinity to infinity of f of t multiplied by f of t plus tau, which is just the correlation of the two basis functions. So if we then take the expression for phi f and substitute it into the equation we had on the previous slide, we get this much simpler expression, this much more simplified equation, which is basically equal to the autocorrelation of the signal vectors, phi s, multiplied by the correlation of the basis functions, or the pulse shapes, phi f. Now remember, I'm not calling phi f an autocorrelation because the pulse shapes are not random. It's just a plain old correlation of two deterministic signals. And so if we look at the equation that we have left, this equation is basically equal to a convolution. So this summation is essentially equivalent to a convolution where we're convolving the autocorrelation of the signal vectors with the correlation of the pulse shapes, or of the basis functions. And that's basically the end of the derivation. So we now have the autocorrelation function that we set out to find. And the last step is to just take the Fourier transform of it. And so this slide shows the result of the autocorrelation. We have the 1 over 2t factor, which was just the constant in front of the time domain expression. This next term, and then we have the magnitude squared of the Fourier transform of the basis function, or basically the Fourier transform of the pulse shape. Now, the reason why it's the magnitude squared is because, remember, in our time domain expression, we had the correlation of the the pulse shape with itself, basically. And when you take the correlation or the autocorrelation of a deterministic pulse, then it's equal to the magnitude squared in the frequency domain. And finally, we have the power spectral density of the information sequence. And the reason why the autocorrelation of the pulse shape term is multiplied with the power spectral density of the signal vectors is because it was a convolution in the time domain, right? So the convolution of these two expressions in the time domain is just a straight multiplication of the two in the frequency domain. And if the signal is memoryless, what that means is that the time domain expression was equal to the energy per symbol multiplied by the delta function. The Fourier transform of a delta function is just equal to 1 in this case. And so if the signal is memoryless, then the power spectral density of the signal vectors is just equal to the average energy per symbol. And so we have a very simple but an extremely important expression. So after all that work, all those equations, all that complexity, we come up with a very simple expression for the power spectral density of a communication signal. And it's basically equal to a constant, 1 over 2t, and a constant, average energy per symbol. And then the only thing that basically determines the shape then of the spectrum of a communication signal is the Fourier transform of the pulse shape. And so the shape of the pulse basically completely defines what the spectrum of a communication signal looks like in the frequency domain. And that's a really important concept. It's a really important thing to remember and take away. And so the last thing I'd like to do is wrap up with an example. So let's use the expression from the previous slide to figure out the power spectral density of a signal transmitted by a square pulse binary PAM modulator. And so this is a picture of the modulator on this slide. The transmit symbols or the information symbols are square pulses with amplitudes of plus or minus 3 volts. So that means the first signal vector is 3 root t. Second signal vector is minus 3 root t, a single basis function equal to the normalized or the unit energy version of the square pulse. And so on this slide, we'll just calculate the terms that we need for our equation. And so the average energy per symbol is equal to 9t. And assuming that the information symbols are independent from one another, the power spectral density of our signal vectors is just equal to the constant 9t, equal to the average energy per symbol. The Fourier transform of the pulse shape, it can be taken directly from a Fourier transform table. So that's where I got this expression. This is to time shift the pulse. This is the unit energy normalization. And then this is the term actually from the Fourier transform table. So the Fourier transform of a square pulse is basically a sinc function in the frequency domain. Taking the magnitude squared, we just get t sinc squared ft. And then putting all of this together, we have our 1 over 2t factor, our magnitude squared factor, our energy per symbol factor, and then this is our final expression for the power spectral density of our signal. It's also very instructive to plot the power spectral density equation that we found on the previous slide. And so that's what I'm showing here. Just a few bits of information about this plot. The first thing is that we assume the symbol interval t is equal to 1 microsecond. On the y-axis, I've plotted the signal in decibels, or dB, and that's a very normal standard thing in communications theory. You always plot the y-axis of your power spectral density on a log scale or in decibels. And the last thing I've done is I've normalized the equation so that the peak of the power spectral density is equal to 0 dB. And that normalization is also, commonly done. And so what we see here is the sort of sinc squared shape of the power spectral density. Now, one thing I'll point out is that obviously this signal takes up a lot of room in the frequency domain. In theory, an infinite amount of room, right? Because the sinc function goes from minus infinity to plus infinity. Practically speaking, when you use a square pulse, you don't take up infinite spectrum because, as the tails of the spectrum decay, eventually you get below the noise floor of your receiver. And generally, once the signal drops below the noise floor of the communication system, we assume that the spectrum is basically zero. However, the fact remains that it does occupy a lot of room in the frequency domain. It takes up a lot of space before it drops below that noise floor. And the decay of the signal is relatively slow. And so generally speaking, this is the square pulse is considered a very poor choice for a communications system because it occupies so much room in the frequency domain. And so later on modules, we're going to look at what better pulse shapes are and how to sort of design a pulse shape in order to have a desired signal spectrum.